Okay, let's go to the next topic, which is polarization of light using transmission. We have already talked using reflection. Today let's use transmission. Okay, when we are dealing with light, remember light is formed by electric and magnetic field. For simplicity, right, we use the electric field as a reference, right? And the electric field is sent in all directions, right? Imagine that light is coming toward us, right? And this should be the direction, right, for the electric field, right? Electric field, imagine electric field is coming, right, toward us, right, in all of these directions. So we said in this case that we say that the light is unpolarized, right? Unpolarized, right? Light is unpolarized. Now let's make it only with moving this field only in one direction, right? Let's make two poles, right? Moving from one pole to another pole, and we call this polarization. How we can make that? Well, we use special devices called polarizers, right? That make pass only one direction, right? Of all of these bunch of directions of the originally electric field, right? So we have, for example, we use a polarizer, right? We have only the electric field moving, let's say, in this direction, right? Up and down, up and down. And we call this linearly polarized, right? Linearly polarized. Polarized. Also, we can take this actually equals to, right? Equals to this representation, right? We have the wave in this way, and we have, right, the electric field, right? We have the electric field, right, in that way, correct? Okay, that's the electric field, right? And of course, these two are the same type of polarization, right? Because we can see this as a plane, right? But when we turn it toward here, right, we see only that, right, moving up and down, right? When we move back again, it's gonna be the wave moving in that way, in a plane or in a line, right? The same idea. So we call this then plane polarized, right? Plane, right, polarized. But these two are the same. Got it? So it's a way how we create polarization. Again, we have to use polarizers to do it. Let's do this case. Imagine that we have this polarizer, right? We have the polarizer, right? We have this as the line of transmission, right? We have the polarizer in this direction, imagine. And we have the lines of propagation, right, of electric field permitted, right, in that way. At the beginning, what do we have? Well, at the beginning, we have this unpolarized, right, ray coming toward this, right, polarizer, right, correct, polarizer. Okay, and then what happens? According to this, only this fraction or this type of light of oscillation of the electric field, right, is permitted, which is parallel to this excess of polarization, right? There's gonna be excess, right, of polarization. And this is the electric field, right, now oscillating, right, let's say up and down, right? It is the amount that is transmitted through the polarizer, correct? Okay, now it becomes polarized, literally polarized. Perfect. Now, what happens if we have a second polarizer? The second polarizer is called the analyzer. Imagine now we have this polarized, linearly polarized light, right? Again, we have a analyzer right here, right? And imagine now we use this electric field, which is parallel, right? Which is parallel to the axis of polarization, right? When that happens, all this light is transmitted through this analyzer, right? Analyzer. Okay, and again we have all this electric field is transmitted, correct? Okay, now what happens if we have an angle? Okay, let's do it. What happens if we have, actually what happens if we have 90 degrees, like this one? Look, imagine one more time, we have now it's gonna be 90 degrees, right? Imagine this is 90 degrees. This is again the axis of polarization, and now we have at the beginning, this is the direction of the incoming polarized, right, electric field. If we have this, right, parallel to perpendicularly to the axis of polarization, right? Imagine that this is 90 degrees, right? When that happens, the electric field coming out, right, through this analyzer is gonna be 0, right? So the electric field in this case is 0. We have no light transmitted. Look, as you can see, if we have a plane, right, the polarizer, if we have, right, light and polarized, right, only, right, the electric field is parallel to this axis is transmitted, right? If we have the analyzer right here, again, and the axis is parallel to the polarized electric field, where we have all the electric field is transmitted, light is transmitted, right? But what happens when it's perpendicular? So no light is transmitted. Means what? Means that the transmission, right, depends on the angle, right? When this electric field is parallel to the axis, we have the maximum, right, transmission. This is maximum, right, maximum. And when we have, right, perpendicular, right, we have minimum. So which function help us to represent this condition, right? When it's parallel, means the angle is 0, is the maximum, and when it's perpendicular, right, the transmission is 0. Which function is that one? Cosine, right? Cosine 0 is 1 is the maximum, right? And cosine 90 is 0, correct? So in this case, we will call this the incoming, right, electric field, right, magnitude. This is gonna be, right, the resultant, right, the magnitude transmitted through this polarizer, right? This simply happen right here. If we have, this is in, right, electric field, it's gonna be out, right, electric field. In this case, it's the same, and right here is 0, right? This is in, right? This is out, is 0. So in this case, we can say that we create a general equation, right? We have that the incident electric field is equals to, actually the out, the resultant, right? The transmission is equals to the incident, right, times cosine theta, cosine of the angle, correct? So we derive this important equation when we're dealing with polarizers, right? We have that this intensity is equals to this intensity, right, times cosine the angle theta, correct? Okay, now again, this is the case when we're dealing with polarizations, Perfect. Now let's go and involve the intensity that we covered in the previous lecture. Let's go to intensity. Perfect. Look, when we involve intensity, remember we used, right, the symbol for intensity, right? Intensity, right? The symbol is S. Also, we can use I, right? Usually we use I, but for this book, the book that I'm using for this lecture, the symbol is S, right? Now, we found in the previous section, right, video, that intensity is defined as C epsilon naught, right, times the magnitude of the electric field square, right? If we apply this to these conditions right here, right, what do we have? The intensity at the beginning of this unpolarized light, in intensity, right, when we have polarized light. Okay, let's do it. So in this case, intensity at the beginning equals to the speed of light epsilon naught, right? Epsilon naught times intensity, right? At the beginning square. The same thing, right, for at the end of polarized intensity, right? Equals to what? C epsilon naught, right? Electric field square. Now let's divide these two, right? Because these two are related, right? By speed of light and epsilon naught. Okay, let's do it. When we divide, right, this by this, right, what do we have? We have that is equals to, look, C epsilon naught, right, out square divided by C epsilon naught, right, in square. And what is this? Well, these two are cancelled, and what do we have? We have that only this is the result. Okay, now let's apply the previous equation that we found, right? When we use this one, what do we have? So it's equals to, right here, intensity in square, right, cosine square theta divided by, right, intensity, right, in square. So these two are cancelled, right? And we have only that S, right, out is equals to S in, right, cosine square theta, right? This is called the Malice's law. Correct. So this is the law that is involved in polarization. Okay, great. So we have the intensity, right, polarized is equals to. This is when we use the analyzer. Okay, cosine. Well, really. Intensity at the beginning times, right, cosine square, right, square theta. Perfect. Great. Now let's see what happens when we're dealing with this equation, right? When we're dealing with this equation, usually we use the average, right? We use the average when we're dealing with unpolarized, right, waves, correct? At the beginning, when we go from this unpolarized wave, right, and we use the polarizer right here, right, the amount that is transmitted, that is polarized, is gonna be the average. And how we can find the average, right? The average, right, is gonna be this average, right? This equals to this times cosine, right, square, right, average, right? When that happens, right, the average for this cosine square is 1/2, right? Cosine square theta is equals to 1 divided by 2. Okay, and then we have that this intensity which polarized only when we go from unpolarized to the analyzer, we get right this result. It's gonna be 1/2, right, the original intensity. Correct? Okay, perfect. In this case, this is unpolarized. Okay, right. This is unpolarized, polarized, and this is polarized, polarized. Correct? Okay, perfect. Now, what happens after that when we use the whole picture? Okay, let's do it. The whole picture is gonna be like this. Look, we have unpolarized light. We have the polarizer, right? This is at the beginning the original one. Well, it's gonna be. We can call for simplicity, right? We can use S naught if you want, but at the beginning instead of in gonna be the same as S naught, right? Gonna be S out. Okay. And then what happens when it goes to this polarizer, right? What do we have? Well, we have now that this intensity is gonna be half of the original one. But what happens if we continue doing, right, using analyzer, right? Imagine we have an analyzer right here, imagine, right? Combined with theta. Now, what happens in this case? In this case, right, we use this equation, right? The Malus law, correct? When we work the angle, we use Malus law. When we start, right, we just use half of the original intensity, correct? Okay, great. So right here, what should be the transmission should be equals to the original one, which is S, right? Original divided by 2 times cosine squared theta, correct? And so on. Got it? Let's do one example. Let's do one example to use these equations. Okay, let's do it. Look, imagine that at the beginning we have this unpolarized light, right, in that direction. Okay, let me make it larger, a little bit larger, right? Unpolarized, right? Okay, like this, perfect. And then we have a polarizer right here, right? This is the axis of polarization, correct? Remember, this is the electric field, correct? Okay, now what should be the polarized light, right, or intensity, right? Well, right here at the beginning is gonna be right intensity in, and now right here is gonna be right intensity out equals to what? According to this equation, right? When it's unpolarized, right? Some polarized, it's gonna be what? This is divided by 2, correct? Now, what happens if we use a analyzer, right, which is perpendicular, right, to this polarized wave, right, in this way, imagine. Okay, now this is 90 degrees. When that is 90 degrees, right, what should be the intensity on the other side? Well, we use the second equation, right, because for second equation, now this is polarized, and also this one must be polarized too. Okay, perfect. So what do we have for this part? We have the final intensity is equals to the initial one, which is what? S divided by 2 times cosine squared theta. But the angle is 90. Cosine 90 is 0. So the intensity is going to be 0 again when the polarized right axis of the electric fields is at 90 degrees respect to the axis of rotation of the analyzer, correct, like in this picture. Got it? Okay, now let's do another example, a general one. Now let's have this example, right? One more time. We have X, Y, and Z, imagine, right? At the beginning, we have the unpolarized, right? Right like this, and then we have a polarized, right? Axis of polarization. Remember, this is the electric field. Hopefully you can see this color. Okay, and then what happens? What is the transmission right here? What is the transmission right here? I mean, this is the incoming intensity, right? This is the outcome, right? Intensity equals to what? Equals to, when this is unpolarized, right? It's equals to 1/2, right? The incident one, correct? Now imagine that we have the polarizer at 45 degrees, right? Imagine, right? Like this. That's gonna be 45 degrees. What should be, right, the outcome? Okay, that one is gonna be, right, this intensity, right? It's gonna be the intensity out, right, equals to, remember, cosine square of 45, right, is equals to 1/2. Okay, now what do we have right here then? We have that this is equals to, okay, the initial one, which is what? Equals to 1/2, right? 1/2, right? Right, 1/2 times, right, cosine 45 degrees, correct? And this equals to the initial one, right, divided by 4, correct? Now imagine that we have another one, but now that one is at 90 degrees respect to this one. Okay, let's do it. Just remember, for the second one, we found that the intensity right here is, right, divided by 4, this one, correct? That's the outcome. Perfect. Now let's go to the next picture. Now imagine that we have this situation. Now in this case, right, this is 90 degrees respect to the original one, or the first one, but not respect to this one. Respect to this one, the difference is 45 degrees, right? As before, remember, if we have only one, only these two, right? At the end we have 0. But because of this one, and because the electric field is a vector, right, we have a component right here in this direction, even though this is 90 degrees, when we place an angle in between these two. Okay, let's see. Look, right here, what should be the outcome intensity right here? Okay, the outcome intensity is equals to the original one times, according to this, right, times cosine square of the angle. But what is the angle? The angle is not 90 degrees. It's the angle between this is the initial one and this one, right, the final one. This is 45 degrees, and now this will be 90. The difference is gonna be 45 degrees, correct? Okay, it's gonna be what? It's gonna be the incoming intensity, right, times cosine 45 degrees squared. But cosine 45 degrees squared is equals to 1/2. So what should be then at the end? This one, the intensity should be what? The initial one, right, divided by 8, correct? Divided by 8. Again, that happens because the electric field is a vector, right? It's a vector. Right here, if we use one more time only these two, the first one and the last one, the difference is 90 degrees, right? The difference is 90 degrees, so we use cosine 90 degrees, of course, gonna be 0, so the last one's gonna be 0. But when we place, right, an extra one, look, we have this at the beginning one, one polarizer, we have another one with an angle, right? And we have the last one like this, right? Can you see it? Because we have component, this has component in, let's say, in the x direction. Got it? Again, if we have at the beginning this one and then this one has no component. But later, if we're right here, this one has a component right in this direction. You see, that's why we have at the end some result. It's not zero. It's gonna be the initial one divided by 8. Can you see it? Got it? And so on. Got it? Okay, perfect. And with this, we finish this section. Remember, we are covering only polarization light using transmission. We have another type using reflection. For that type, that is covering higher levels, especially, right? We use the Brewster angle, right? But don't worry about it in this chapter, right? For us, right? Later we're supposed to use for reflection. You wanna check it later, right? You wanna learn more reflection, right? Case polarization by reflection, right? It's gonna be, pay attention, the Brewster angle. Brewster's right angle. Okay, and with this we finish this chapter. See you in the next video.